Google it because somebody stole it and put it in internet, but anyway, it's, if you want the sort of corrected version, I can send it to you. So that's basically a course on this subject, what I'm going to talk about, except for the next week's, but this week's stuff. I think I can start.
Well, at least I can introduce
Okay.
Kupiainen. We're very fortunate to have him here in Paris for a month, and he's going to give the last series of lectures so on quantum field theory for probabilists.
Yes, and I see that there are lots of non-probabilists here who are not supposed to be here. This is a course for probabilists, not for physicists, for instance. So let me go to the, while waiting for, I don't know what we are waiting, but quantum field theory originally was created as quantum theory of quantum fields, of field theory in the 30s of electrodynamics, basically. So infinitely many degrees of freedom. And after that, it was in the 50s sort of got also into statistical physics, into condensed matter physics, and ended up in the 60s sort of a unification where quantum field theory and condensed matter statistical physics were unified under the concept of Renormalization Group. So that was on the physical side, and of course, ever since it has been used everywhere in many instances of physics, and there has been discussions on whether how one actually should physically describe quantum field theories. It depends a lot on what one is going to apply them to. If you're interested in that, there's a nice preprint by Greg Moore recently where he discusses critically various problems in quantum field theory. Okay, on the mathematical side, immediately in the 50s, it was understood that this is an interesting subject because it sort of seems to have, is mathematically challenging to make sense out of. This the field of axiomatic field theory was created at that time. In the 60s and 70s, there was the field of constructive field theory, where actually exact examples of quantum field theories were constructed. After that, most activity was probably in geometry and topology. So it started with index theory and ended up probably with Langland's program. And then, I suppose, during the last 10 years, within probability, there has been some interest in quantum field theory, mostly in two-dimensional quantum field theory related the developments starting from SLE. People realized that there was actually a physical subject about this, the conformal field theory, and that was certainly interesting for probabilists. And then quite recently, stochastic partial differential equations with very rough noises has been realized by probabilists that there's a lot of similarity there with quantum field theories. Okay, so this last, one could give 10 courses each 2 semesters on quantum field theory on various aspects, and I have basically today 2 hours minus 15 minutes, and tomorrow Wednesday and 2 hours, and next week 2 times that. So I'm not going to give you any full course in quantum field theory of any of these aspects. The only thing I want this week to explain, try to explain a little bit what are the divergences in quantum field theory, and what is renormalization group, and how that deals with that. Okay, this will be completely heuristic, no mathematics. Going to give you the picture, and then next week, this picture we are going to do again in a mathematically rigorous manner in the context of stochastic partial differential equations with rough noises. So equations like KPZ in 1 dimension, and Glauber dynamics in 3 dimensions and 2 dimensions and things like that. So that's my objective, is to say a few words about divergence and renormalization with that in mind. But I think I should still waste about a little bit time just to bridge bridge the sort of connection to probability starting from quantum field theory. So quantum field theory is supposed to be quantum mechanics. And what is quantum mechanics? At least there has to be a Hilbert space. There's also usually energy, which is a positive operator. And when we're talking about quantum field theory, there are also fields. So fields are creatures which live on space and space-time. Okay. So t is time and x is in space, depending on which dimension you are interested in. And the Hamiltonian tells you the temporal behavior of the fields. So the temporal behavior is given by this formula. So the semigroup of the Hamiltonian tells you about the temporal behavior of these fields. And then there is one very special state, namely the lowest energy state of the Hamiltonian, which is usually called vacuum. Okay. So that's the minimum maybe what one could have in quantum field theory. There are symmetries. Quite often one talks about Poincare asymmetries, conformal symmetries, gauge symmetries, whatever. But there is no probability, okay, here. On the other hand, probabilists know about random fields. There are various instances of that, but let me just, for this course, we are just taking the simplest possible setup. So I have, these are random variables, or random fields, taking values in. Okay, I forgot to say what these are supposed to be operators, okay, sorry. Acting on the Hilbert space. Okay, so there's nothing probability there. We have a Hilbert space, we have operators, and their time evolution. Here, the fields are supposed to be not exactly functions, but let's say, let me call differently the dimension here. They are distributions, okay? And we usually talk about them through the, for instance, through the characteristic function. Let me call it S of f, where I have some test functions. And then you can do various things depending what you are interested in. But if you are interested in bringing the going towards quantum field theory, there's one extra. Well, usually you assume some regularity, okay? Regularity with this map. I won't go to any such details now during this week. I'm just going to give an impressionistic picture. But there's one thing which connects from here to here, and that's the concept of reflection positivity. And and that to go to that, you basically, let me give you basically sort of abstractly. Think about now, we'll try to think about our space-time here. Let me put the time here and the space here. And then let's think about the positive times. So let's take fields which are located here. So let me take test functions. So these are functions whose support is in the t positive. Well, let's call it x0 and x, okay? No, x1 and x, okay? Okay. So let's take such which are support here, so in R plus. Okay, let's take such test functions, and let me look at the span of all the fields, the span of all these vectors. Okay, so I'm looking at all the. This is a real number, so I denote by phi of f the pairing between the element in S prime and S. Okay, let me put it. I try to be consistent here with phi of f. So let's look at all that and do the following. Let me call by theta the time reflection. So if I take a test function anything, and there is x1 and x, so this is going to be the time reflection. I'm calling this time. It's not really a time. It's just the first coordinate here. And let me assume here that it's stationary. The field is stationary. In the x1 direction.
Excuse me, phi of f is function on the half line.
This is the half space here. So
Phi of f is function
on f. Phi is a distribution. F is a test function.
So phi of f is a number.
Yeah, this is the dual pairing between distribution and these are. I'm looking at all the linear combinations of these objects.
It's numbers.
Yeah, but I mean I'm working in L2 of my probability space. Okay. Okay, so I have some probability space. Okay. I'm talking about random fields. Yeah? Okay. So let's look at the time reflection. And the reflection positivity is the following condition. So this is an extra thing. Not usually when one thinks about probability, one thinks about generating function. They are functions of positive type, right? And there's a little twist to this. You take test functions and their reflections. They form a matrix. Any number here, and takes these guys in the F plus, S plus. And you demand that this matrix, this is an n by n matrix, demand this to be a positive matrix as a matrix. Okay, that's reflection positivity. Okay, why is this nice? I mean, if you ever looked at how Stone's theorem, for instance, goes when you have measures and they're generating functions. There's a variation of the same story here. You look at, you take now this linear space here, and you make out of this thing now a scalar product. So let me define for f and g in F plus. Let me define the following scalar product. Let me see. So f and g equals, you take expected value of, you reflect the f, the complex conjugate. So both of them live here. This you reflect to there, and then you take that. Okay. That's a sesquilinear form, and this reflection positivity implies that this is actually scalar product. Okay. This condition is exactly the thing you can easily check, which guarantees that this gives non-negative norm. So now you just divide by the null vectors. And take the completion of that, and that's the Hilbert space of the quantum field theory. Okay? All right. So that's the first thing here. Hamiltonian comes in a similar way, namely, if I have now operators here. So if I have an operator which maps this positive these fields here to the fields there, and if I now go down to here, and if the O respects this condition here, then let me call it O tilde, an operator acting in the Hilbert space. Okay. Simple example is a time translation. So time translation is just the following operator. I take any of these guys, F. Let me just let me take it. Let me just take one of these guys and define it to be e to the I phi translated F. That clearly takes you towards the right there. And it's very easy to check that it respects this descent here. And it has various properties. It clearly is a semigroup. It's very easy, again, to check that it's a semigroup with norm less than or equal to 1. After all, here you are just translating. Translating, so this looks completely non-preserving. Looks at least not non-increasing, and that's easy to check. It's actually a continuous semigroup, and it can be written since it's a continuous semigroup. It has a generator, which is our physical Hamiltonian. Generator will be non-negative, and the vacuum state will be just the vector 1. It's a pi of the vector 1. Okay. So that's how you go. I mean, once you have this extra condition on your random fields, you have stationarity in the first direction, then you end up this field theory description. Now you can define the quantum field by this relation here. So let me call it phi quantum, T and X. I just define it by taking the field at 0 first component. This is all probability. So if you call probability imaginary time, depends whether you start with physics or mathematics. One is imaginary. This is imaginary time physics, yes. We are getting to the real-time physics now with this formula here. So you take the field here. And that's your quantum field. Okay. Another. This is just time translation.
Yeah, yeah, but
This is not trivial. This is highly non-trivial, of course.
time translation just
In that picture, yes.
yeah.
Let me go.
Okay.
Let me go to the example of the free field in a second, so you will see. Okay. But before I close, I mean, this is supposed to be prelude, okay? And this is really not going to be. Don't want to go into much more details here, but the connection is the following. So you start with a probability. You have this extra condition, reflection positivity. This is actually the condition which usually comes from statistical mechanics models. And that condition then allows you to sort of do this construction of the state space of the quantum mechanical system and the operators. And then the connection to how you get from back to the operator, connection between the two objects is the following formula. So if I take these quantum fields, let me put them like this. And look at their expected values in the vacuum state. Then these are actually, and let me take this, these are actually analytic functions. That's because of the spectrum condition on the edge. Okay, so if I take these as the first coefficients here, the times complex numbers, then there's analytic boundary values of analytic functions where the imaginary parts of the times are in the increasing order. And you can then analytically continue them. And if I give this some name, it's usually called the Whiteman function. So these are actually analytic functions of the t's in such a region. And then this Whiteman function at imaginary times, as was just said. Equals just the probabilistic object. So that's the story. Okay. Originally, axiomatic field theory started by looking at these Whiteman functions, starting with the axioms for quantum fields, realizing that these are analytic functions because of the spectrum condition for the Hamiltonian, analytically continuing them and realizing that you get actually probabilistic objects here, and then these probabilistic objects were the topic of constructive field theory then in the 60s and 70s when one actually tried to construct concrete examples of quantum field theories. Now, I'm sorry? Yes. Yes. So I took an example of the operator as the time translation. And then you check that it descends here. You check that the operator has these properties. So as a consequence, it's given by, it's a semigroup with a positive generator. And the generator is the H. You need to check continuity, but that is a strong continuity of the semigroup. That's easy to check.
If you define H to be there, it is self-adjoint.
Then it's self-adjoint. It's positive, actually. Yeah. Okay. Good. So that's a story, and that's a big story. If you're interested, there is a book from the 70s which discusses this in great detail. I think it's a reasonable book by Glim and Jaffe. All right. let's do an example, the free field. And I'm not really doing the example very much. Time, yes. So depending on which direction you want to go. If you start from probability, then the first coordinate is becoming imaginary. If you start from physics, then also the first coordinate is going imaginary, okay? And he called it imaginary time because he starts from physics and then he makes his physical time imaginary. But if your probabilistic time is something important for you, then the physical time will be imaginary, okay? Free field. Well, that's Gaussian. Gaussian measures. Gaussian measures, of course, are described by their covariances, right? And this reflection positivity condition, then since that's completely explicit, it's easy to check that it's just that this covariance is reflection positive. As a matrix. Okay? So here I use scalar product. Okay? I mean, please stop me if the notation is not clear, because that's okay. So covariance operator, if satisfies this condition, then you have reflection positivity, and then it's not so difficult to end up that basically the interesting examples are just the following. The covariance operator in this setup where we are is just the following operator. So Laplacian is the usual Laplacian, and this is m squared is a positive non-negative number, and what else? That's it. Yeah.
So excuse me, at the end of the day, we get to measure, or we get a process, right, the random process on the space of distribution.
Yeah, okay, so free field. Let's have a Gaussian random field. So Gaussian random field for me is something whose generating function is exponential of such an object where C is the covariance of the random field, okay, covariance operator. So this defines with, if C has some regularity in the distribution space, this defines you a random field, which I call the Gaussian random field, okay? And then this extra condition on that field combined with, okay, so here, to get this, I should put here translation invariance also in space and rotation invariance everywhere. It still doesn't fix this. You get finally, if you put all these invariances, you get a linear superposition of such guys. But the most interesting example for us will be just this covariance. So that's the free field mass M free field. Okay. Two exercises. This is completely concrete, okay? Now, do this, okay? The first exercise, this Hilbert space, which was gotten by this abstract procedure here, everything on the positive side and divided by zero known states. It has a concrete description that, as L2 space of a certain measure. And the measure is just the law of this field at time zero, the imaginary time at zero. So you just take the original field, which lives everywhere, and take it here. And that law is very explicit. It's, of course, Gaussian. Well, it's just you restrict this random field with that covariance to there, and it's a Gaussian with covariance. And this is your exercise to do this. I mean, it doesn't require much work. Covariance 1 over, well, let's put it half minus Laplacian plus m squared to the power minus half. And this is now in this space or d minus 1. Okay, that's a nice exercise to do. And the second exercise, I'm putting them as exercises because I'm not going to need any of this stuff. This is supposed to just give still background. You can compute the Hamiltonian also in a concrete form. And it's enough to compute what it does to these vectors. And it's given by the following. Let's give a name to this operator. I will call this 1 over 2 times E. E for energy. It's called energy because this is the relativistic energy by Einstein. The momentum squared plus mass squared square root. That's the energy. And it's given by just this formula. Both of them I'm using exercises. Both require doing one integral, okay? One Fourier integral. Once you have that, then you can start the course on quantum field theory. This formula is something which is called second quantization. Namely, the quantum field theory Hamiltonian acting like that is sort of related to the action of just one particle, the Einstein's energy in the sort of physical space, and creation and annihilation operators and all that. Okay, we are not going to go to that. Fock space and so on and so on. All we are going to do with this is to apply the Feynman-Katz formula. To get non-Gaussian examples. Okay, I describe you here general formalism, a simple example, the free field. And of course, both in physics and mathematics, we would be interested in something more than just the free field. And one way to arrive at this to just start from this free field. So we have the free field, which is with its Hamiltonian here. And everything in the free field is just dealing with the time zero field here. Okay? So let me take some function from this time zero field. So S prime of r to d minus 1. And let it be bounded from below. And again, I'm very vague here, but we'll do a very explicit function in a second. But let's suppose you have something like that. And now you would say that, okay, maybe we get interesting theories by not taking this free field, but just perturbing it by this V. Okay? And you can do it, okay, of course. And if you in probability, if you have studied a Feynman-Katz formula, you know how to proceed. You just do the following operation. you do the Trotter product formula first. And then you do this construction what we have there. Let me put it like that. Okay, and let me like that. And then I write that as follows. And e to the minus sum over p over n sum over v at t v at let's put it like that, phi j t over n. Okay, and tt. Okay. If I now I can start commuting this here, and then I get the v at different times. So this equals in the limit as just e to the minus integral from 0 to t, v at phi t dot dt. Okay, times t and the whole field. That's the Feynman-Katz formula. So, you get sort of a path space version by going t units in time. And that brings us then to I'm sorry? I'm not commuting anything. You see, here I translate first this unit of time, then I do that, another unit of time, and if I can, this is pushing me t over n towards right, okay? Then I take the v at time 0, then push again and take the v. That corresponds to having the v at these times if I push immediately to the time t. There's nothing else than that. Okay? So let's suppose that this operator has again a unique lowest spectrum state, ground state. Suppose I have such a thing. And then we had, of course, let me call it omega 0 the vacuum of the question of the unperturbed system. Then I can do the following calculation. I put omega 0. I compute e to the minus t h plus v, and take omega 0 here. And let's put here e to the t times e. And let's take a limit as t goes to infinity. Then by spectral theorem, I just pick the vacuum here. So this by spectral theorem, this goes just to the inner product of these two states. Okay, as t goes to infinity. On the other hand, this thing I can write with my Feynman-Katz formula as expected value of e to the integral from 0 to t v of phi of s dot ds. Okay? So what does this give me? Okay. So what does it give me? So if I do look at the following probability law, which is by definition the limit as t goes to infinity. Some normalization, let's call it zt. To normalize it as a probability. And let's put here from minus t to t, okay? And here is the probability law of the original free field. Then I expect this to be a quantum field theory in the sense we have been describing, with Hamiltonian just this h plus v minus e. That's what this calculation here tells you, okay? You add to that Hamiltonian that corresponds on the probabilistic side by perturbing the original law by the Feynman-Katz formula here. Okay? Yeah. Okay. Sorry. That's energy. What about scripty? Okay. So let's assume that this new Hamiltonian also, this operator, this is a bounded from below operator. Let's assume that's bounded from below because V was. Let's assume that it actually has a unique lowest point in the spectrum, unique state there called omega and so on. Okay. Concrete example. Let's take this function v, just the following. Let me put it lambda times integral over r d minus 1 of phi x to the power 4. I'm sorry? Yes. Well, no. Good question. Yes. Good question. So with this V, okay, with the proviso, okay, reflection positive proviso. Yeah. So Feynman-Katz formula I can do, of course, with arbitrary V, and I will get some measure. Now the question is whether the measure is reflection positive, and with this V it will be the case. Okay. Very good. Reflection positivity, of course, involved comparing time reflections, and if you have something which is non-local, some function which is non-local in the phi, you could screw that up. And at the moment, I'm just taking something which is completely local, and that will be okay. Yes? Local means that it's local in the exponential in the Hamiltonian. Locality here means that it's the action functional is local. Okay, you look puzzled. Maybe we come back to this in a moment. Just if you wait for a second and I write you a formula. But let me take such a function. Then I expect to try to construct the following measure. Let me call it nu d phi. I take the limit as t goes to infinity. The limit as some box goes to rd minus 1. And I normalize by some number. And I take this thing here. Okay, and I take here the Gaussian measure with this covariance C, free field. Okay, you take the free field covariance in d dimensions. You take such a perturbation, and you normalize by that. By locality, I mean that the thing which is here in exponent is a local object, so it's an integral of local objects. You can sort of see that the time reflection, once you think about this depends on the fields everywhere in the universe, right? But it's sort of multiplicative in the sense that it's a product of something which is on the negative times and a product with a product of something in the positive times, because exponential is this additive up here, so it's multiplicative downstairs. Reflection positivity was a condition exactly of this form. You are still puzzled? Okay, so all of this is supposed to be motivation that interesting quantum field theories could be obtained by perturbing around the free field by taking such objects. Yeah? Yes. Depending on the dimension. We come to that in a moment, okay? Yeah. There are subtleties here. There's one problem which is called the ultraviolet problem. And that's dealing with the fact that this Gaussian measure lives on distributions. So phi is a distribution, so it's not obvious what it means, what is phi to power 4. Okay? You can't multiply distributions together. And then there's the infrared problem, which is the problem of having here these integrals which run over unbounded regions. And as we will see, they are both very much related to each other. So the rest of today and on Wednesday will be basically a study of this thing. I want to explain to you first today what are these divergences, what are the problems here, by very simple perturbation theory. Then I will tell you what are the rigorous results known about these things. And I want to explain to you how to look at this from the point of view of statistical mechanics, namely scaling limits of statistical mechanics models. And then tomorrow, on Wednesday, how all these things can be understood by something which is called the Renormalization Group. Okay? So today, our objective will be just to see how these problems arise and what is known about these things. So now you can forget about everything about that and just let's decide that we are interested in studying this stuff. Okay?
Before we forget, we took a free field. Can we take of the
Yes, you can study such things. But reflection positivity is not true for instance, for the fractional power, or if you take square of Laplacian, it's not going to be reflection positivity. So you will not have a unitary quantum field theory on the physical side. But if you are interested from point of view of probability, you can, yes. No, I told you that the only reflection positive guys which are also Euclidean invariant are just these free fields, okay, the Gaussian ones. That's it. It's a superposition of them. You can put take over M exactly with any measure. Okay.
U of d phi at the end of the day, this limit. What is this object? It is measurable.
This is supposed to be an interesting measure in the space of distributions. Okay. We want to show that this measure weakly converges to something interesting. Okay. Okay, so for next week's stuff, from this week, I think it's the philosophy is the thing which I want to convey. Because next week we are going to do then, using this philosophy, something on stochastic partial differential equations. But it's important to absorb the philosophy, not all the details of these calculations, because as I told you, this is a course. So you can look at the lecture notes, which I have. If you want, I can give them to you for details. But I mean, I want to try to get a little bit of the philosophy. And one way to get into is to start doing perturbation theory. And this is, of course, if you take a course in quantum field theory, this is a major subject. This is the subject of Feynman graphs, Feynman diagrams, and all of that. Okay. And again, we are going to just do very, very basic stuff of it so that we get into to see. So the first thing we need to do is regularize everything. We are supposed to take fourth power of distribution, etc. So that's not going to work as such. So we regularize. Okay. So the first regularization I will do, I call it ultraviolet regularization. One way, I'm going to use two different ones completely interchangeably. The first is lattice. So I replace RD by discrete points, and regularization parameter is epsilon. And then also infrared regularization, meaning that I put everything to a finite box. Okay. All right. Then I will take the free field with covariance C epsilon. It's still the same thing, but now I'm using the Laplacian 1 over epsilon squared sum over F like that, where I is of length 1. Just the discretization of Laplacian. Maybe there is a half also because I'm summing over positive and negative guys. All right, so that's the Gaussian measure, and then the measure we are interested in is the perturbation of it. Okay. This is the measure we are interested in. Okay. The other regularization I'm going to use is in momentum space, Fourier space. And it will be much more convenient in many calculations. So if I look at this free field operator, this is of course different. This is an integral operator with integral kernel given by the Fourier transform of 1 over p squared plus m squared. Okay. Okay, and I will regularize that by taking the Fourier multiplier there. Some nice cutoff function. Okay, something like that. Okay. Good. And then I would take nu epsilon lambda to be 1 over, again, z epsilon lambda times e to the minus lambda integral over the volume phi 4 mu c epsilon. If I regularize like that, then this Gaussian field is almost surely smooth function, and there is no problem of writing down anything like this. Okay. What should we do with the break? Yeah, we can have it now. So the rest of today will be want to show you how these things blow up in 2 dimensions. Very simple. How they blow up in 3 dimensions, slightly more complicated, and how they start to blow up when you go to 4 dimensions, more complicated. Okay? And then we want to finish by seeing what is the connection of this object to things which you might be familiar with, for instance, the Ising model. So that's that today. And tomorrow then we do something to justify these claims which I'm going to make today. So let's have a 5-minute break. Yeah. There's something puzzling? Or?
No, he was asking for the potentials, what you put here. So this, you can put any polynomial bounded from below?
In 2 dimensions. In 2 dimensions.
Why?
Once you
but in 3, no?
Once you weak order it in 2 dimensions, you can put anything.
Yeah, but in 3 it's going to explode.
In 3 you can put up to 6 power, but no more. And in 4 you can put only the 4th power.
But people always look at this, not other Hamiltonians. I mean.
Oh, in physics you might have all kinds of examples, but this we'll see by universality and renormalization group that this is all you need to look.
Oh, this.
Yeah.
So
this.
And if you're not bounded from below, there is no criterion.
Well, physically you want the energy to be bounded from below. But again, of course, I mean, sometimes you can be interested in that, and then, of course, you can try to do something. Yeah.
So if I put an exponential, it's okay.
Yes.
Exponential is fine.
Really
That's in 2 dimensions, but not more than 2.
Yeah.
No, but there was an issue with the Hogg code, what they call the Hogg code thing.
Hofcode, yeah.
Hogg
Hogg.
code. You know, the Hogg-Krohn model.
Oh, Herr-Krohn model. Yeah, that's 2 dimensional. Yeah, but
there was an issue of it in Simon's book saying something's not right with this model.
Well, no, Herr-Krohn model is completely okay, but I mean,
It's trivial or whatever.
no, in 2 dimensions we know exactly what it is, right?
Yeah,
we have been studying it, okay? But in more than 2 dimensions, there were claims in the old days that you can do it in 4 dimensions and get a non-trivial field theory. And they were in 4. 4 is the one which is interesting for physics. Okay? And there was a claim that you can do that, and actually there were several proofs, and they were all wrong in the sense that the theory what they finally constructed was the Gaussian free field. Because once you renormalize it, it inevitably becomes the free field. But indeed, during the time of Simon's book, there were claims that such
No,
things
but what
didn't.
I'm talking about is in 2 dimensions. Simon's, he says we don't want to study it because it's not interesting physically.
Oh, maybe because his
Because it's positive or something. No.
no,
No, but
No, it's fine.
no, it's fine, yeah, but he has a sentence, which is weird.
Yeah, I forgot now. I can imagine that that time the whole issue was that 2 dimension is the first step to go to 3, and 3 is the first step to go to 4.
Yeah,
okay?
so since there's no 3 dimension.
Since there is no way to do this, I mean, the 2 was considered utterly unphysical, okay? 2 was what the mathematicians were dealing with because they couldn't deal anything else. And
but it's still that way today.
yes.
We haven't changed.
Yes.
Excuse me. So minus delta plus m squared is an operator, and you apply it to x and y.
Yeah. No. That's the fundamental solution to the equation minus Laplacian plus m squared, the Green's function. Okay, so you want to write f equals f of x equals integral dy, Green's function of x, y, g of y. Right? Okay, and this Green function, which is the inverse of this operator. Yeah. And by Fourier analysis, it's just Fourier transform. Its Fourier transform is this. Okay.
Basic question. So I have not known the reflection positivity. Sorry, but I wonder if what is the kind of finite dimensional analog for this.
Finite dimension.
Yeah.
Well, in statistics. Well, on the lattice.
On the lattice, yes.
Yeah, it's exactly the same. Then the Hamiltonian exponential of the Hamiltonian is the transfer matrix of the statistical mechanics model. Okay.
That's fine.
Yeah. Time is discrete, so you don't have any more infinitesimal semigroup. I mean, if you are on the lattice.
No, so I'm talking about the reflection positivity.
Yeah, reflection positivity is the condition on the lattice. On the lattice you can take one of the axes and do exactly the construction what I did. And you can construct a positive inner product there. Yeah. And then the time translation is actually just a transfer operator. Take Ising model on the lattice, okay? Okay. It couples nearest neighbors, and you have to now check that it's reflection positive. It's not automatically, that's a condition which you need to check. But Ising model satisfies it.
Oh, okay.
Okay, and then once you have that, then the formalism goes through, and you get the time translation is given by some operator, and that operator is just what usually we call the transfer operator of the Ising model. So
I'm thinking about, for example, some kind of one-dimensional lattice model, like Heisenberg model. Maybe
yeah, same thing. But you are talking about.
There's a kind of connection between XXZ spin chain and ASIC, right?
Right. Yeah.
This looks pretty similar to that.
Yes.
I wonder what is the connection.
Yes.
And especially, I wonder what is the.
In spin chain, you are immediately given the Hamiltonian. Okay. Yeah. Yeah. I mean, there you can have a continuous time, right? You have continuous time and discrete space. Right. So if I had completely discrete everything, then I could get just the transfer operator, not the Hamiltonian, because there is no infinitesimal time. Right. Yeah. But once you are on the spin chain, like you start immediately with the Hamiltonian. So it's really already starting with the Hamiltonian. Okay, and then you're asking the question, how do I go back to this sort of space-time picture? Yeah. But it's by the same formula again.
Okay, maybe that's also
maybe, but maybe we can continue. Yeah.
Maybe for that case, maybe having non-positive of diagonal elements are important.
Non-positive, yeah, but your Hamiltonian is still. But your Hamiltonian. But okay, you're. Okay, well, maybe we can discuss it. Yeah. There were many questions. One question was, why would one consider just this for instance. Why should it be local? Why should it be non-local? From the renormalization group, we will get justification for all that maybe on Wednesday. For many instances, this is all you need to construct by universality. And in this particular setup. So, and the non-local things will be, in a certain sense, completely irrelevant. We're going to see that later. But at the moment, let's just take it for, let's decide that let's try to do this and see what happens. Now I have either way, somebody was asking what is this object? This is the integral kernel, so that's the green function of this problem, okay? The minus Laplacian plus n squared inverse. It's the green function of this elliptic equation, and it's given by this Fourier integral, okay? If there are any questions of my notation, because there are all kinds of concepts here, and just stop me, okay? Okay. Now we are going to be interested in correlation functions. So the expected values of products of these fields. Once I have done all this regularization, all the fields are almost surely smooth functions, so no problems with anything. There is no infrared problem because I put myself into a box. Everything is well-defined finite, okay? I will use the physicist notation because it's very much better than the mathematicians with brackets for the expected values, okay? Okay, so once we start, and I have this what I call coupling constant here. When lambda is 0, I'm doing nothing, and now turn lambda on and ask what happens. So when lambda is 0, there is nothing to say. This is just the covariance of the Gaussian free field, and it's this function, let me call it Cx minus y, and it's given by this function here. And C has an epsilon in it, okay? Okay, so C is a function whose Fourier transform explicitly, let's use this momentum space cutoff. So Fourier transform is this, okay? And I'm using the discretization. I'm not using the. I told you that I will even in the same line jump from one to the other, okay? Depending what is more convenient to write down, okay? But at the moment, let's use this regularization, okay? In the Gaussian case, of course, hopefully everybody knows how to calculate this. Let's put it like that. So let me call this 0, meaning that lambda equals 0, okay? So in the Gaussian case, this is just given by sum of the pairings of the points and product of product of the covariances of the pairings. I hope this formula is familiar from elementary Gaussian measures. So the covariance completely determines all the correlation functions. They are just sums of products where the sum is over always to pair these two and x's here. I call it script p as the pairing. Now, perturbation theory, the physicist perturbation theory is just Taylor expansion in lambda. When I have put all these cutoffs here, then these correlation functions are actually smooth functions of lambda, and I can compute their derivatives. Let me do that. Okay, let me use the notation that V equals this lambda, this integral over the volume phi x4. Okay, and I'm supposed to compute the Taylor coefficient. Lambda equals 0 of phi x, phi y with lambda. Okay, so by definition, it's dn d lambda to the power n of phi x, phi y, e to the minus lambda v, 0 divided by e to the minus lambda v. So far, so good. I'm supposed to take derivative of that and put lambda to 0. Okay? And this has a simple formula also in probability. This is just, there's a minus 1 to the power n times the cumulant of phi x, phi y, v. By cumulant, I mean the following. Well, cumulant is just a shorthand for that, but it's explicit expression. So cumulant of v f1 and f2, for instance, is just f1, f2 minus f1, f2. Cumulant of f1, f2, f3. And you start subtracting. And then you get, what do I get? 2. And so on, okay? What's important there is that they are basically just expressions of involving such objects. Okay. This cumulant involves such objects. And by this formula here, wherever it is, we are just supposed to pair all these. So this thing here equals minus 1 to the power n, sum over pairings. And those pairings can be identified with graphs. So this is sum over pairings, obviously. And the identification is the following. If I have a pairing, that gives rise to a graph with vertices. So vertices x and y and x1 up to xn. Okay. And edges, well, pairs of these vertices where the edges, such edges are allowed. So multigraphs, if you wish. Okay. So what do I get? I get minus to the power n, sum over all such graphs which are connected. That's the secret of the cumulant. Connected of something which I call the amplitude of the graph. And the amplitude of the graph is some numerical factor times integral lambda to the power n dx1 dxn, product of this C bi minus bj vertices. Okay? Sorry, edges. Okay, so that's should be pretty obvious. Okay, if I just look at this object, I'm supposed to pair all these guys, but I can also pair the x1 to itself, so I can have such a thing in the graph. And then the thing which of course requires some checking, which I'm not going to prove to you, is that the cumulant here forces all these graphs to be connected. So instead of doing graphology for hour or two, let's just look at examples, which is all we are interested in at the moment. So let me look at examples. Okay, so let's look at, I'm going to look at only the two-point function for a while, lambda. So what do I get? Okay, if I have nothing, no insertions, then I have just such a graph, so that this is Cx minus 1. Okay? Then the next one, you do the combinatorics. There are 12 as the number, and I get this graph. Okay? Then on the second order, you get more graphs, so you get such a graph. And I will not compute the numbers. Okay. Plus order lambda cubed. Okay. So let's look at this. This we understand, that's the free field. The first correction, let's write it explicitly. Once you write one of these explicitly, then everything else is clear. So let me write that. This is by definition, this formula, integral over x1, running in the box lambda, covariance from x to x1, then covariance from x1 to itself, and then the covariance from x1 to y. So this is nothing but this is here is 0, so this is C of 0 times the convolution of C with itself. Okay, and C of 0, sorry, it's C of epsilon all the time, but I'm forgetting to write this epsilon here. What is C epsilon of 0? Okay, so we have the formula there, so it's integral. Let me use this cutoff e to the minus epsilon squared p squared over p squared plus m squared. So this is obviously something, and we are in d dimension. Let me put it here. It's completely convergent at convergent integral, but it blows up as epsilon goes to 0 as something like so it goes more or less like epsilon to power 2 minus d. D is bigger than 2, some constant, and log epsilon. Good. So that's, there we see the first divergence, and we also sort of not so difficult to see how to cure it, because all you do is the following: you renormalize. By which I mean the following: it's not a good idea to use this guy as the perturbation. It clearly blows up. Okay, even the first order in this perturbation expansion blows up, so looks hopeless. So let's change it by the following. Let's add here something, let's call it rho times phi squared. Okay. If I do that, then I get, of course, other graphs. I get graphs like this. So there's a row here. Graphs like that. Graphs like that. Whatever, okay? If I have a phi squared, then I get similar expressions here. Instead of 4, I get square. And I can have vertices in my graph which have just 2 lines coming into one vertex, okay? Well, if I now choose the row, let me choose the row as minus 6 lambda times this C epsilon 0. Then this graph gets multiplied, gets subtracted, will be okay. Okay, so what do I mean by that? Let me say proposition, very easy proposition. If I add that term, then nth derivative lambda equals 0 of this phi, and you do the same thing. It has graphs with no they are not anymore these multigraphs. So has only graphs which have no these nor these. Okay, they just drop out. Okay, so let me put the definition. I call the weak power of phi to the n. Will be the following expression. So d to the n. We return to this later, but let me put here the definition. And again, in probability, this is of course a familiar concept. It's basically certain Hermite polynomial in the phi. And so what we constructed here with that particular row we normal ordered. This is called normal ordering or weak ordering of the interaction. Yes? I'm sorry? Statement of the proposition is the following. If you do this, what I said, and compute the nth derivative at lambda equal to 0, just like I did, then you get a similar expression, but you have graphs which don't anymore have this such things. I'm sorry? Simple graphs, not multigraphs, yes. They get cancelled by this, just like every time you have such a thing, you would also have such a thing, and that thing was just done so that that gets. It's very easy combinatorics. Again, I'm not going to do that, but you can amuse yourself of proving that almost nothing to do. Okay. Okay. So proposition, another easy proposition. I'm not going to prove either. So now I'm in 2 dimensions. Okay. So as epsilon goes to 0, this phi n. So I define this. So this is a random field, right? We have the cutoff epsilon, so this is a smooth random field, like everything has been smooth. But as epsilon goes to 0, things blow up. Nevertheless, this converges to a random field. To S prime RD valued random field, R squared. Random field. Okay. So what does it mean? It means that if I take a test function and integrate the thing against text function, then and take the expected value of this guy to any power k, this is finite. Let's just do the example k equals 2. So let me compute expected value of integral of fx phi x4. Let me compute the variance of this random field. By these manipulations here, it should be pretty obvious to you that this is the following graph. I have for one vertex and another vertex, and I join the lines, and only this graph is left. And how does this graph behave? It behaves as the fourth power of the Gaussian free field covariance, which goes like logarithm of x minus y, the power 4. That's an integrable function. So we are completely in business. So corollary of this, the perturbation theory coefficients. So let's write it like that. Have epsilon going to 0 limits. Okay. And the limits actually are nice distributions. So all of that is very easy. The hard theorem is the following. And this goes back to Guerra, Rosen, and Simon in the 70s. It's the following. So let P phi be any polynomial in phi bounded from below. So it means even degree, and the highest coefficient positive. So not only the phi 4, somebody was asking, why do I get phi 4? At least in 2 dimensions, I can take any polynomial. Then the measure, this measure, I normal order the polynomial, and we know how to do it. And I multiply it by this Gaussian measure with covariance C epsilon. And strictly speaking, now we are on the lattice regularization, the theorem. We normalize it. This has a limit, converges weakly as lambda goes to ZD, RD, R squared, and epsilon goes to 0 to a measure nu. Measure on S prime. Arbitrary coefficients. in particular, these limits contain all the unitary conformal field theories in 2 dimensions. In 2 dimensions, all you need to do is to do the Wick ordering, yes, normal ordering. But we'll come to that, okay, with the renormalization group later. But this sounds much better than what it says. It just says that the limit exists. It doesn't tell you at all, for instance, what they are they critical, non-critical, etc. Okay, but everything is included somewhere there. But and this is proven using correlation inequalities and various tricks which work only in semi-bound. The P is bounded from below. So in our case, lambda has to be positive. Okay. All right, let's go to 3 dimension. We did 2 now. Yeah. No, series. I've forgotten now the series. Okay. Okay. Series was just this combinatorics. We have the perturbation theory and coefficients. Easy thing is to prove that the coefficients converge. Okay. I did use some example. I did use the simplest example. That's easy. The theorem here is nothing to do with perturbation theory. It's completely non-perturbative theorem. Okay. The only thing which you learn from the perturbation theory that the only renormalization you have to do is the normal order. But perturbation theory is not involved in the proof at all. The proof is that you are on the lattice and you're taking continuum limit of the lattice using correlation inequalities. And it's a long story. We are not going to go to that. And if you're interested, there's a book by Barry Simon in the 70s dealing with this. Okay, let's see what happens when we go to D equal 3. Okay, well, in D equals 3, this C epsilon 0 went like constant A times 1 over epsilon. But apart from that, I told you that already that the normal ordered object is a random field, well-defined random field. Well, let's go slowly, okay? So this gives order lambda in perturbation theory is okay, because I just canceled the divergence. Let's go to the second order. I erased the graphs probably, but there was one here. There's the one. All these are pretty harmless. This drop out, okay, because by the normal ordering. So only this is a new graph for 2-point function. Let's write the expression for that. Well, here is x, here is y, x1, x2. Concretely, this is cx minus x1, cx1 minus x2 cubed, cx2 minus y. Integral dx1, dx2. Right? That's our rules. In 2 dimension, how does, well, this depends on epsilon, but we are interested in what happens when epsilon goes to 0. How does the green function of Laplacian behave in 2 dimension? Well, it's the usual Coulomb potential. So x1 minus x2 is a linear power. So if I take it to third power, the third power here, this is not an integrable function in 3 dimension. Okay, so this blows up like actually log epsilon. As epsilon.